Hello and welcome to the third part of this measurement series on the process of analytical chemistry measurements. Today, we're going to be taking a look at chemical measurements and errors. So we're going to be talking through some of the relatively common equipment that you might see in a chemistry laboratory, some things that you might be utilizing, some equipment which is useful in terms of measuring or dispensing quantities of especially liquids and solutions. We'll be talking about errors that exist within these measurements, such as random errors and systematic errors, and also some ways that we can mitigate these errors or we can overcome them and ensure that our calculations are accurate. So a little bit of an outline. So we'll first be considering safety, which should always be our number one priority whenever we're doing any kind of chemistry, whether that be analytical or otherwise. We'll also be talking about some common analytical chemist lab equipment, although some of this is relatively universal. We'll be dealing with significant figures, so we'll be talking a little bit about what significant figures are and how we deal with those in different calculations. We'll not be going into a lot of detail there, but we will be discussing them as to how they pertain to our analytical chemistry measurements. And then errors in analytical and instrumental chemistry. So a lot of these errors occur in measurements or they occur in terms of our instrumental analysis. And so they must be overcome in order to ensure accuracy and reliability of our measurements and our results. So the first thing is we're going to talk a bit about safety. So safety requires advanced planning and preparing for any hazards involved before starting. So whenever we first plan out our experiments or our methods for our measurements or our reactions, we must always consider each step and think about which steps might introduce specific hazards and plan for them and try to mitigate any potential difficulties they may cause. So do not start any procedure until adequate safety precautions are made. Do not assume that just because you're a particularly skilled chemist or a scientist that you will be safe from any hazards. It's not always the scientists themselves, but sometimes the other scientists in the lab can also introduce hazards to your safety. So be familiar with safety equipment such as goggles, fume hood, lab coat, gloves, emergency shower, eye wash, and fire extinguisher. So make sure you know where all of these things are. Make sure that you have adequate containment. The scientist on the right-hand side of the frame here, they have, as you can see, safety goggles on. They're using containment measures in the fume hood. They have a lab coat. They have gloves. And so they are well equipped to start their experiment or their measurement. Chemicals should be stored and used in a manner that minimizes human contact. So this usually involves storing them in a specially designed cupboard or container. Before using any chemical, ensure that environmentally acceptable disposal procedures are established. So this means that before you use something, make sure that it can be disposed of in a way which will not adversely affect the environment. And label all containers that contain chemicals so that anyone who is unfamiliar with what is happening in the lab cannot accidentally risk their own harm by not knowing what's in a particular container. So we'll talk a little bit now about some of the common equipment that we find in a lab. So the first one is going to be the lab notebook. And so this is going to be a record of all the things that the scientist or the analytical chemist has done and observed. And it is important that it's recorded in detail, any observations, any results. And it should also be written in a way that is understandable to other people so that the work can be repeated by anyone. Often a considerable amount of your day will be spent actually writing in your lab notebook. And this can seem tedious and unnecessary, but 6 months down the line, it may be difficult to remember exactly what you did whenever you got that result, which is now of interest to someone else within your organization. So often a lab notebook in many jurisdictions is a legal document, and especially in industrial settings, it typically has to be countersigned by your direct supervisor at the end of the day to sort of acknowledge that you are the one that has conducted these experiments and that your observations are yours, so that in any future creation of maybe a patent or whatever, then you can be properly credited. So scientific truth in research. So this is the idea that in the lab notebook, we're telling the truth, no matter whether the result is good or bad. We're always trying to ensure that the observations are correctly recorded. There's no such thing necessarily as an incorrect observation, so long as the observation is correctly noted. So first of all, we need to state what was done, then state what was observed, and then make sure that it is understandable to someone else, because some projects may extend well beyond your tenure with a particular organization. And so the lab notebook stays with the organization, and it may be given to someone else who works on this project after you. And so that they should be able to understand what is going on. And so the greatest error made by scientists is writing incomplete or unintelligible notes. And so this is something that should be avoided. It's often something that's relatively easy to do, is to sort of think, oh, maybe tomorrow I can write into my lab notebook, but it's really just better to make sure that you spend an adequate amount of time recording what you have done. Electronic balances are another sort of integral part of most chemistry labs, or labs that are involved with analytical measurements, because they allow us to accurately measure different masses of a compound or a sample, different quantities. So an object with mass m is placed on an electronic balance, much like the one here on the left-hand side, and this pushes the pan down with a force mg, where g is gravity. So we can see here the scientist is placing a mass or an object onto the balance. It's well, their fingers are in the way right now, but there is a reading here displayed on the electronic display of the balance, and this is relative to the mass of this object. The mass of the object obviously is acted upon by gravity as well. So the balance produces an electrical current to exactly cancel the motion of the pan. So as the weight of the object pushes the pan down, there is an equal and opposite electric current produced, which is what is effectively used to measure the mass of the object. So the current magnitude is used to measure the mass on the pan. So one technique that can be utilized is this idea of weighing by difference. So for compounds which are hygroscopic, that they particularly absorb a lot of water or moisture from the air, it's often necessary to try and reduce the amount of exposure they have to the air. If you are able to do these measurements in a moisture-free environment, that's great. But if not, a way that it can be mitigated is through weighing by difference. So what will happen is that we tear our weighing scales, our electric balance, and that is just to set the container with the pre-dried sample or chemical inside of it, set that at 0 grams. And from that, then we can quickly remove some of the sample into whatever receiving vessel that we will utilize in our experiment or our measurement. So we transfer the dry reagent from the bottle to the receiver. Then we close the weighing bottle and reweigh it. And this negative value here is the amount of mass which has been removed from the original bottle. And so this corresponds to the amount of mass that was removed. And so this is going to be the amount of mass that was delivered from the bottle to the receiver. And so this is weighing by difference, and is a very important technique which can be utilized to try and mitigate the kind of disadvantages of hygroscopic reagents. And there are many reagents which are quite hygroscopic, and they rapidly absorb moisture from the air. So reducing weighing errors. So we locate the balance on a heavy table. Sometimes a marble slab is used, or you could use basically any piece of flat stone or something, to just so long as it's heavy, to minimize vibrations from the building. This becomes particularly important whenever the balance is located higher up a tall building, because generally the vibrations are larger at the top of a tall building versus the bottom. This can be due to sort of like atmospheric effects amongst others, especially if you live near maybe a train station or something, or the lab is near a train station, then the vibrations from the train going by can also cause errors in the weighing. Keep level and recalibrate after any level adjustments. So if we are going to move or change the location of the electronic balance, it's important that it has been recalibrated after any level adjustment. Always make sure that the sample is centered on the weighing pan. Measure the samples at ambient temperature. So whatever the room temperature happens to be, whether that's 20 degrees Celsius, 25, 30, make sure the sample is also at that temperature. So if we take a sample from a refrigerator or a freezer, we must let it equilibrate with the ambient temperature. And if it comes from a colder temperature, then it's a good idea to keep the sample in a desiccator to keep it dry, and also to reduce moisture accumulation inside of the container. So close the balance doors to prevent drafts from altering the measurements. And then tweezers or tissue are recommended for placing objects on a balance to avoid fingerprints, because with very, very small quantities, sometimes fingerprints can have a significant effect on the mass of the sample to be measured. Volumetric flasks are also commonly found in analytical chemistry laboratories. They're utilized to produce solutions of a known volume. So their volumetric flasks are used for the preparation of solutions with known volume. Transfer pipettes deliver fixed volumes, so these are less accurate. Measuring pipettes deliver variable volumes. So the transfer pipettes deliver fixed volumes. So these are pretty accurate, and less accurate ones are measuring pipettes. They're kind of a similar structure to volumetric flasks, or sorry, burettes, which we'll also talk about shortly. So larger volumetric glassware has smaller relative uncertainty. Serial dilutions should be designed to make a dilute solution from a more concentrated solution. So usually, it's easier to make a dilute solution from a concentrated solution, as we learned in the earlier parts of this course, rather than a concentrated from a dilute. From a dilute, you need to, from a dilute going to a concentrated, usually you have to remove some of the solvent somehow, maybe by heating it to evaporate the solvent. Volumetric glassware can be calibrated by weighing water added. So since the volumetric glassware is sort of specific to a particular volume. I mean, if we have a 1 liter volumetric flask similar to this, these are Erlenmeyer flasks, but this here is a volumetric flask, and it will have a gradient somewhere along here. Maybe this is a 1 liter flask, and if we measure to or fill this to that line, we will have 1 liter of volume inside of the flask. So since our distilled water or pure water has a density of around about 1 gram per milliliter, then we can add water here until we reach the limit here. And then based on the mass of the water inside of the volumetric flask, we are able to calibrate our glassware. And so this is particularly important whenever we really, really need to be very accurate with our volumes and our concentrations. Burettes then. So burettes should be read in a reducible or reproducible manner and drained slowly for best results. So if we open the tap completely and the volume of liquid flows through too quickly, it can often be uncontrolled and we can end up with less accurate results. So read between markings to obtain accuracy 1 decimal place more than the graduations. So the graduations in this particular example are every 1 milliliter or every 1 centimeter cubed. And we can read in between those to get maybe a 0.5 or 0.6 or 0.7 reading for our accuracy. So our accuracy can take into account the space between the markings. So the first step in using a burette is typically to wash it with fresh solution. So we get one of the aliquots and we wash through the burette to sort of coat it with the solution that we'll use to remove any of the chemicals that might have been used in cleaning the burette. Then we eliminate any air bubbles in the burette before use, just to make sure that the volume in here and the volume that we use as our starting point is actually all the solution and it's not partially air. So there could be a little air bubble trapped at the bottom whenever we have a solution up to the, say, like here at the 10 milliliter mark, could be a little bubble down here, and that would push up the meniscus higher than it actually should be. So then after that, whenever we're starting our transfer of solution or liquid, we want to drain slowly so that we are in control of the process. Then at the end, we'll add a fraction of a drop near the end point of our titration. We'll read the graduation here from the bottom of a concave meniscus. Typically, we're using water as our solvent, so we'll be utilizing a concave meniscus. And then we estimate the reading to 1/10 of a division as best we can. So in this case, each division is 1 milliliter. So maybe we would read to, in this case, maybe 40.1 or 40.2. Then we try to avoid a parallax, and then we account for graduation thickness in our readings. So whenever we're doing all of these measurements, we're doing the mass measurement on a balance, we're doing the volume measurement on using a burette, and so on. There is a degree of uncertainty. There is, unfortunately, no perfect or way to read a true value. We're simply reliant on the absolute accuracy of our equipment, and oftentimes we need to calibrate our equipment in some way. So we can often try and do that by accounting for our relative uncertainty. So relative uncertainty is the uncertainty in a quantity divided by the magnitude of the quantity. So it's really how much we can trust the value. So relative uncertainty is expressed as a percentage. So percentage relative uncertainty is the uncertainty in the quantity divided by the magnitude of the quantity times 100%. So typically this is why the larger volumes have a reduced amount of uncertainty, because generally the uncertainty in a quantity doesn't change based on the volume, but the magnitude will. So larger volumes decrease the percent relative uncertainty. So if a burette has an uncertainty of plus or minus 0.05 milliliters, and if we then deliver 20 milliliters and then 40 milliliters each, the percent relative uncertainty in the volume is delivered is so the volume added. So if we add 20 milliliters, then our calculation will be this uncertainty, which is 0.05, which we got up here, divided by 20, which is the volume that we delivered, times 100%, will give us a relative uncertainty of 0.25% in our final volume measurement. Whereas if we add 40 milliliters, the uncertainty doesn't change, but the magnitude of the quantity does change. And so the relative uncertainty is roughly half of what it was. And so we end up with a considerably more accurate volume reading. And so this is why it's easier to avoid relative uncertainty with larger volumes. A pipette then, so pipettes are used to transfer known volumes. So a pipette such as the one here is one that has a graduation mark here or a calibration mark. And so the volume is known specifically for this. So it is a known volume. You cannot really accurately measure out volumes of different amounts. You would need different pipettes. But for a particular volume, say 20 milliliters, then this would be a very accurate way of transferring. So this is a transfer pipette, and it is calibrated to deliver one fixed volume, and the last drop is not needed. So oftentimes whenever we pipette out the volume, so we pipette in the volume from one place, and then we transfer it to another, we pipette to this graduation line. Whenever we expel the liquid into its, or deliver it to its new container, there will often be a small drop in the bottom. This drop does not need to be removed because the pipette has been calibrated based on the idea that this drop will remain. And so we shouldn't try to force it out in any way and should just discard it. So here's the calibration mark. We fill to this line whenever we fill the transfer pipette so that we know whenever we deliver to its new container, it will be that amount. So a measuring pipette is calibrated like a burette, so it will have graduation marks, but it will be filled and the liquid will be expelled in a similar way to this one. Transfer pipettes are generally more accurate though, because they are calibrated specifically to a certain volume. And so it doesn't rely on graduations or human systematic error or human random error to ensure that it's accurate. So micropipettes, such as the one here, which we often see in biological applications, these can have big errors unless recently calibrated and used with excellent technique. So really, whenever you're using these sorts of pipettes, you really need to be a particularly skilled user to ensure that you try to mitigate any systematic errors in your measurements. They also tend to lose their calibration pretty quickly, simply because they have a lot of moving parts. And these moving parts kind of will affect the overall accuracy of the measurement. They'll sometimes get moved out of place through overzealous use or through incorrect storage and things like that. So it's important to keep them well maintained and well calibrated. Experimental error then, so all measurements have an associated error. There's no real way to get a true value of anything. We can, as I said earlier, we can only get the best value, to the accuracy of our equipment. So the better quality and the better calibration, or the more recent calibration that we have for our equipment, the more accurate value we can get. But the true value of anything is often very difficult to obtain. So the best practice often involves applying a technique that from experience is reliable. So if we in the lab are very familiar with a particular technique, we usually are very skilled in that technique. And so therefore it is more or less going to be a pretty reliable way to measure something. Rather than trying to develop a new technique or a new skill, it's often best to just stick to what is reliable and what is going to give us the best or the closest measurement of this value. Repeating a measurement with the same method allows determination of its precision or reproducibility. So we'll find out that if we measure something 5 times and we get roughly the same result 5 times in a row, that indicates that the precision or the reproducibility is going to be pretty good. Accurate results are those that produce the same value with different methods on the same quantity of material. Significant figures then are an important consideration whenever we are doing our analytical or instrumental measurements. So addition and subtraction. So the number of significant figures is based on the number with the fewest decimal places when all exponents are equal. So for example, if we add these two values together, we will get a value which has got the same number of significant figures as that with the fewest decimal places. So both of these have the same number, and this is the final value that we get. For multiplication and division, significant figures are limited by the factor with the smallest number of digits. So here we have 22.50 multiplied by this number, which will give us 50.90 after we have corrected for the significant figures. So that's kind of how we would do it in addition, subtraction, and multiplication and division. Logarithms then, so these are things whenever we're dealing with, especially the most common one, I guess, in analytical chemistry that we deal with in logarithms is going to be the pH scales or any of the P scales. So for logarithms, the number of significant figures is applied slightly differently. So generally, the only part of the logarithm answer is going to be significant is going to be the mantissa, and this should be the length of the mantissa should be equal to the number of significant figures in the original quantity. So for example, if the pH of a solution, or sorry, what is the pH of a solution that is 0.0235 molar in H3O plus? So this is our relationship of pH to H3O plus concentration. So the pH is equal to the negative log to the base 10 of the concentration of H3O plus. Remember that these square brackets indicate concentration. So we will fill in our concentration value from the question. So pH is equal to minus log of this value. So we have 3 significant figures in our answer, which means that our mantissa should be 3 figures as well. So our pH is going to be 1.629, where the mantissa, this part in bold, the part after the decimal point, is going to be 629. That's 3 significant figures, which matches the 3 significant figures that we have in our original quantity. Rounding then, so this is something that's very important with calculations with many digits. So usually whenever we're doing calculations, we want to keep more digits than strictly necessary and only round off at the correct number of digits or to the correct number of digits or the correct significant figures at the end of the calculation. This will help us to ensure that we keep a reasonable degree of accuracy throughout the calculation. So at the end, whenever we're about to report our final answer, we'll want to consider all the digits beyond the last place desired. So that's usually say we have 3 significant figures, so that will be after the 3rd significant figure. So the 4th digit and beyond will be used to consider the final answer. So we round up if the excess numbers are more than halfway to the next higher digit. So for example, in this one where you have 23.94743, this would be rounded up to 23.95 because the number here is beyond halfway to the next number. So the next number for this number would be 5, and so that's why we get 23.95. We would round down if the insignificant figures are less than halfway. So for example, 23.944 is rounded down to 23.94 since 4 is less than halfway to the next number. Now, if we are exactly halfway between a number, we round to the nearest even digit. So for example, 2.55 is rounded to 2.6 because it is halfway, and then the next even digit is going to be 6, so 2.6, and then 2.45, that's going to be rounded to 2.4 because 2.45 or the next digit would be 2.5, which is odd, so we round to the next nearest even digit, so that's going to be 2.4. Random and systematic errors. So random or indeterminate error alters the precision or reproducibility of a measurement. So this is usually an error which we cannot directly account for, we cannot determine the origin of, and is present in all measurements. So it's caused by uncontrolled and uncontrollable variables in the measurement. So sometimes it's related with measuring from a particular scale or otherwise. And so we cannot necessarily control it, but we can account for it. Unfortunately, because it has an equal chance of being positive or negative, it is not going to be the sum of all of the errors. And it cannot be avoided. It's always going to be present. But like I said, there are ways of mitigating it. So systematic errors then are determinate errors, and these affect the accuracy of a measurement. They are typically caused by equipment flaws or experiment error design or design error, but they're often reproducible, so they can be overcome. So systematic error causes can be determined and eliminated, but some random error is always going to be present. So no matter what we do, we're still going to have a certain degree of error. And we always strive to eliminate systematic errors in all measurements. So how do I detect a systematic error? Or how do I account for it? So one of the ways to do it is to analyze a known sample, such as a certified reference material. So typically these have been analyzed in detail. They have a very specific peak position or quantity or size or mass. In some way, they are very reproducible. They have been reproduced by many people in many different places, in many different situations, and they give the same reliable result. And so we can analyze that in our own instrument. And if we get the same result, then we don't have much of a systematic error. But if we do have a different result, then we can utilize the differences here to try and account for our error. Now, we can also analyze blank samples. So these would contain no analyte being sought. And so a non-zero result here means that the method corresponds to more than you intend. So we end up with, for example, an extra 0.1 or 0.2 to our measurement. It means that we're going to end up with a result higher than we would have expected. So typically you see this in things like UV vis spectrometers, where even blank samples, because of light leakage into the container or into the sample holder area, because of that light leakage, sometimes there is like a background signal. And so we need to know what that background signal is before we can actually measure our sample. And so usually there are ways and means of mitigating that already built into the instruments. So different analytical methods can be used to measure the same sample, and if the results do not agree, there is error in some of the methods. So this is the idea of using multiple different instruments to try and measure the same sample to try and get the same result. And if it's not possible, then there's going to be error in one or both or all of the methods that we have used. Another way is round robin experiments. So really what we're doing here is we're giving the same sample to different people in different labs and asking them to analyze the samples in different ways or using the same methods. And then we compare the results from each one and we try to analyze and see if the method that we are using in our lab is reproducible and is accurate. And if it's not, then we can try and mitigate the potential causes of those errors. And then any disagreement beyond the estimated random error is going to be systematic error. Uncertainties in random error. Random error associated with a measurement can usually be estimated or measured. So error is expressed as the standard deviation of the mean, or as a confidence interval. So we'll learn about those more in a future section where we'll talk about standard deviation, how that's calculated, and how we can use it. Then with random error, it is assumed that systematic error has been detected and corrected. So for random error propagation, for most experiments, arithmetic operations can be performed on several numbers, each of which has a random error. So it depends on exactly what or how the system is being added together, or if it's being multiplied, or what the operation, the arithmetic operation is, on how we actually determine the random error. It's not going to be the same every time. So uncertainty of a result is not the sum of the individual errors because they have an equal chance of being positive or negative. This causes some cancellation of errors. And so the way that we calculate this is, as I said, not going to be the sum, because if we have one that's positive by 0.5 and then the next one is negative by 0.5, we would end up with an error of 0, which is not how it works. There's always going to be a certain degree of error. And if we do multiple steps, the errors will compound and they will be combined together in some way. So for random errors, propagation of uncertainty in addition and subtraction requires absolute uncertainties. So that means that we are creating the sort of the total sum of those. So here we are squaring the errors, which will remove any negatives. And so we'll only have positives. And then, so here we're squaring error 1. So say we have a two-step operation. So we have error 1 and error 2. We square those to remove any negatives and then take the square root of the sum of this to obtain the absolute uncertainty. So the absolute in this means like the total, like the magnitude of the value. Then if it's multiplication and division, we utilize the relative uncertainties. And so here we have the relative uncertainty of step 1 plus the relative uncertainty of step 2, both of which are squared, and then take the square root. So we will have the error in multiplication and division steps. So there are some rules with that. So here are the ones that we saw just a moment ago for the addition and the subtraction. Then we also have for multiplication and division. And so these are using the absolute uncertainties. Here we have the relative uncertainties. And then we have some rules here for other functions. So for example, y is equal to x to the a, where a is a constant without uncertainty. We would use this uncertainty relationship. Then we have here y is equal to log x. So this is the kind of thing that we would utilize for our pH measurements, for example. And then we have some others down here, which will be useful whenever we are trying to manipulate different equations as we go through on our analytical and instrumental chemistry journey. So uncertainty propagation example. So how exactly do we utilize these rules in a particular question or a particular problem? So here's an example of that. So what is the uncertainty in the volume delivered from a burette if the reading uncertainty is plus or minus 0.04 milliliters and the initial reading is 0.10 milliliters and the final reading is 19.64 milliliters? So if we have 19.64 milliliters plus or minus the error minus 0.10 milliliters, we can obtain the total volume transferred, which is this 19.54 milliliters plus or minus the error, which we are being asked to determine, or the uncertainty. So the uncertainty here, because these are addition, or these measurements are, this is a subtraction, so we're getting the absolute uncertainty, is going to be 0.04, which is the error in step 1, or in measurement 1, and then the error in measurement 2. So we're going to get those squared and then added together, and then the square root of that will give us the absolute error. So the absolute error is going to be 0.057, but then we have to correct to our significant figures, which is going to be 0.06. So it's less than the errors added together, but it's more than the individual error. And so the uncertainty in the volume delivered is going to be plus or minus 0.06 milliliters. Here's another example. So this time we're going to be using some of those log rules that we just saw in the second part of those rules. So what is the percent uncertainty in the concentration of H3O plus? So we're looking at acid concentration here. If the pH is 3.87 plus or minus 0.02. So we first rearrange our equation for pH. So the pH equation is here. So pH is equal to minus log concentration of H3O plus. And so that then can be converted into H3O plus concentration is equal to 10 to the minus pH. And so this is our, I suppose, looking at it is our rearranged equation. Just did some mathematics. We put the negative sign on this side, then we removed the log, and then we went through to this. concentration of the acid is equal to 10 to the minus pH. So then we can fill in the pH value here, which we got in the question. So H3O plus concentration is going to be equal to this, which will give us a value approximately 1.35 times 10 to the minus 4 moles per liter. So from the tables that we saw on the previous slides, this equation is y is equal to 10 to the x. So y is going to be our H3O plus concentration, and x is going to be the pH value here. So the rule that we'll use is this, which is e to the x over y is equal to 2.3026 e to the x being the error. So the error in the H3O plus concentration is what we're trying to find out. Divided by the H3O plus concentration is equal to this. So we can, so this is then going to be equal to the error in the pH. So the error in the pH is going to be this. So it's 2.3026 times 0.02 is going to be equal to 0.0461, which is going to be our sort of value for this part here. So then we can substitute values in. So we find that the error here in H3O plus divided by H3O plus concentration is equal to the error in the H3O plus divided by 1.35 times 10 to the minus 4, which is the concentration here. And that's going to be equal to this value that we just calculated. So it's going to be here. So that means that our error for our concentration is going to be 6.2 times 10 to the minus 6 moles per liter, which is much smaller than the concentration we calculated here. But that's really fine because generally we want our error to be smaller than the value of the absolute value, or like the larger value of our concentration in this case. So the concentration of H3O plus will be equal to 1.35 plus or minus 0.0622 times 10 to the minus 4 moles per liter. And so that means that we have a pH uncertainty of 0.02. Gives an error of 5%. So this is the pH uncertainty is 0.02. This gives an error of 5% in our H3O plus concentration. So systematic error propagation. So systematic error often occurs in common situations, such as molecular mass calculations and volumetric glassware calculations. So it is treated differently from random error in arithmetic operations. So for systematic uncertainty, uncertainties are summed from each term in a sum or difference measurement. So systematic error in the mass on n atoms of one element is n times the uncertainty in the mass of that element. So say the uncertainty is 0.5, we have 2 atoms, so the systematic error would be 2 times 0.5. So uncertainty in molecular mass with several elements is calculated from the sum of squares of the systematic uncertainty for each element. And so let's see that in action. So uncertainty in the molecular mass of O2 So the average mass of O2 is somewhere in the range of 31.9988 plus or minus 0.008 grams per mole. So what's the uncertainty in this? So the uncertainty in the mass of n atoms is going to be n times the uncertainty of one atom. So that's going to be equal to 2, which is the number of atoms in molecular oxygen, times the relative uncertainty, which is this 0.008, which is going to be equal to plus or minus 0.0016. So the uncertainty is not as it was for the random error. So it's not going to be the absolute uncertainty, which would be this value here. So it would be the square of the uncertainties. The absolute value would give us plus or minus 0.001. So for systematic uncertainty, we add the uncertainties of each term in a sum or difference. So another example of systematic error propagation. So if a 20 milliliter class A, which is a very high class grade of a volumetric pipette, is certified to deliver 20.00 plus or minus 0.04 milliliters. So the volume delivered is in the range of 19.96 to 20.04 milliliters. If the uncalibrated pipette is used 5 times to deliver a total of 100 milliliters, what is the uncertainty in that 100 milliliters? So how accurate is it? Like, do we really get the 100 milliliters? Or what is our error for the serial addition of 5 times 20 milliliters? So the uncertainty here is going to be a systematic error. So the uncertainty in 5 pipette volumes is plus or minus 5 times 0.04, which is going to be equal to plus or minus 0.20 milliliters. And it's not going to be the absolute error, which is this, plus or minus 0.09. So you can see here this random error, if this was a random error, would be a lot smaller than the systematic error that we get from this measurement. So you can see that smaller volumes typically have larger errors. So the difference between 20 milliliters and the actual volume delivered is a systematic error. It will always be the same. And so if we calibrate our pipette, this will eliminate or greatly reduce our systematic error. Calibration and systematic error then. So how can calibration of a particular instrument or piece of glassware really help us to reduce the amount of error in our measurements? So if we have a calibrated pipette and this delivers a mean volume of 19.993 milliliters with an uncertainty of plus or minus 0.005 milliliters, and we deliver 5 aliquots, the volume delivered is going to be 5 times 19.993 milliliters, which is going to be equal to 99.965 milliliters, with an uncertainty of plus or minus 0.011 milliliters. And so this uncertainty is going to be here. So the error in the volume delivered is going to be equal to the absolute error of each one of the measurement or each one of the aliquots delivered from the calibrated pipette. And so that's going to give us this value of 0.011 milliliters. So for an uncalibrated pipette, we just have systematic error and the uncertainty would be much larger. It would be 5 times 0.03 milliliters, which would be equal to 0.15 milliliters, which is our kind of standard error for a pipette of this size and this type. So delivered volumes, so this would mean that the delivered volume would actually be quite different for the uncalibrated pipette from the calibrated one. The calibrated one would really quite accurately deliver this 99.965 milliliters, whereas the uncalibrated one would show a relatively large amount of error, and it could be anywhere from 99.85 right through to 100.15 milliliters. There's sort of a difference there of 0.3 milliliters, which is not an insignificant volume. So in summary then, so safety is the #1 priority, and we must plan for any and all hazards which may be encountered during the process. Note-taking is especially important to ensure reproducibility of results. Systematic and random errors are always present, but both can be accounted for. Random errors are always present, and calibration can reduce the effect of systematic errors. Okay, let's check comprehension. So what is the uncertainty in a volume delivered from a burette if each reading has an uncertainty of plus or minus 0.2 milliliters? Please pause for more time if you need it. Try and work through it on your own, and then we'll go through it together. Again, pause for more time if you need it. Okay, so you might have noticed that we weren't actually given the initial or final readings of our burette before and after the volume was delivered, but this isn't strictly speaking necessary because we're only being asked what the uncertainty in the volume delivered is. We're not asked what the total volume delivered was. So here we have the error of the final and the initial. So the error of the volume delivered is going to be plus or minus this E. E is then going to be the absolute of all of the errors of the steps. So the two measurement steps are the initial and the final. So it's going to be 0.02 squared plus 0.02 squared. Square root of that will give us an error of approximately 0.028, which whenever we deliver to our correct significant figures will be 0.03. And thus the uncertainty in the volume delivered is going to be plus or minus 0.03 milliliters. Thank you for watching this. Make sure to leave any questions or comments you have down below, and we'll see if we can address those. Bye-bye.